Here is a beautiful problem from the International Mathematical Olympiad shortlist. For any prime number p, we need to prove that we can find another prime q with a special property. No matter what integer n we choose, the number n to the power of p minus p will never be divisible by q. Let's rephrase this using modular arithmetic. We are looking for a prime q where the congruence n to the p is congruent to p has no solution. Before tackling the general problem, let's solve the simplest case, when p equals 2. This will give us some intuition. When p is 2, we need to find a prime q where n squared is never congruent to 2. In other words, 2 should not be a perfect square modulo q. Let's test q equals 3. Let's check all the possible squares modulo 3. Since 4 is congruent to 1, the only possible results for n squared are 0 and 1. The number 2 is not a square modulo 3. Therefore, n squared can never be congruent to 2. So for the case p equals 2, we found our prime. Q equals 3 works perfectly. Now for the main event. We'll assume p is an odd prime. Our strategy is to construct a very specific prime q that has exactly the properties we need. Here is the plan. We are going to find a prime q that satisfies two conditions. First, the order of p modulo q is exactly p. A direct consequence of this is that q must be congruent to 1 modulo p. And second, q is not congruent to 1 modulo p squared. That's an excellent question. We will now prove that such a prime not only exists, but we can construct it from p itself. Let's define a number n as p to the p minus 1, all divided by p minus 1, which is this sum. We will choose q to be a special prime factor of this n. Since q divides n, it must divide p to the p minus 1. This means p to the p is congruent to 1 modulo q. The order of p must divide the exponent p. Since p is prime, the only possibilities for the order are 1 or p. Let's assume the order is 1. This would mean p is congruent to 1 modulo q. If we look at n modulo q, each p becomes a 1. Summing p1s gives us p. So n is congruent to p modulo q. But we started with q dividing n. By transitivity, this means q must also divide p. Since they are both prime numbers, this forces q to be equal to p. However, if we look at n modulo p, all terms except the first are 0. So n is congruent to 1 modulo p. This means p cannot be a factor of n, which contradicts our finding that q equals p. Therefore, our assumption was wrong, and the order must be p. Now for the second property. Let's look at our number n modulo p squared. All terms from p squared onwards are 0 modulo p squared, so n is congruent to 1 plus p. Now, assume for contradiction that all prime factors of n are congruent to 1 modulo p squared. If this were true, their product, which is n, would also have to be congruent to 1 modulo p squared. But we know n is congruent to 1 plus p. This leads to the absurd conclusion that p is a multiple of p squared. This contradiction proves our assumption was wrong. We have successfully constructed a prime q with both of our desired properties. Now we just need to prove that this specially chosen q actually works. We will use one last proof by contradiction. Assume for contradiction that there is some integer n where n to the p is congruent to p for our chosen q. Since we know q is congruent to 1 mod p, q minus 1 over p is an integer. Let's raise both sides to this power. This gives us n to the p. All to the power of q1 over p is congruent to p to the power of q1 over p. The left side simplifies to n to the power of q minus 1. By Fermat's little theorem, the left side is just 1, so 1 is congruent to p to the power of q1 over p. This means the order of p must divide the exponent, q minus 1 over p. But we chose q specifically so that the order of p is p. So p must divide q minus 1 over p. This implies that p squared must divide q minus 1, which means q is congruent to 1 mod p squared. But this is a direct contradiction. We deliberately chose q so that this would not be true. Let's summarize our elegant argument. The assumption that there was an integer on, for which the congruence held, led us to a contradiction based on the very properties of the prime q we constructed. This means our assumption was false. For our special prime q, no such n can ever exist. Since we successfully constructed a prime q with the required properties, we have proven that such a prime exists for any pqed. Thank you for joining this exploration of a classic IMO problem. If you enjoyed this video, please like and subscribe for more mathematical content. See you next time.